This lesson is on half-life. So what is half-life? Well, a radioactive isotope eventually will decay and it will turn into something else. The half-life is the amount of time it takes for half of a sample of a specific radioactive isotope to decay and turn into something else. So a half-life is really just a time. It's a time, so it's measured in, say, like 2 minutes or 5 minutes or 10 minutes or 20 years. So the half-life is how long does it take for half of a sample of a specific isotope to decay. So a few examples of radioactive isotopes and their half-lives. Radium-226 has a half-life of 1,620 years. So if you have a sample of radium-226, 1,620 years later, half of it will actually be lead because it had decayed into lead. And then another 1,620 years after that, another half has decayed. So now you're down to only a quarter of what you started with, and most of it had turned to lead. Uranium-238 has a half-life of 4.5 billion years. Now, how would a scientist even measure that? We'll get to that near the end of the lesson. Chromium-51 has a half-life of 27.7 days, and francium-221 has a half-life of 4.83 minutes. So you can see that different isotopes have completely different half-lives, ranging anywhere from less than a millionth of a second to more than 1 billion years. One thing that's important to mention is that the half-life of a specific isotope is completely independent on external conditions like temperature or pressure. And it also is independent on the amount of atoms present in a sample. So you could have a sample of 1,000,000 moles of a specific isotope and it would have the exact same half-life as, say, 1 mole of an isotope. So one thing you can do is you can go to ptable.com, and if you click at the top tab where it says isotopes, you're able to click on any element you want, and what you will get is either a selected group of the major isotopes of that element, or you can click on the button, the radio button that says all of the isotopes of that element. And then if you hover over each isotope individually, you can see the half-lives of the different isotopes. So for example, carbon-14 has a half-life of 5.7 times 10 to the third years. If we hover over that, and that is going to undergo beta minus decay after 5.7 times 10 to the third years, half of a sample of carbon-14 will undergo beta minus decay. So now if I click on zinc, I'm able to see the major isotopes of zinc. So if I first start on zinc-64 is stable. Zinc-65 has a half-life of 244.06 days. Zinc-66 is, let me check here, stable. Zinc-67 is stable. Zinc-68 is stable. Zinc-69 has a half-life of 56.33 minutes, and Zinc-70 is stable. So you're able to check out the different isotopes of each element and determine what their half-lives are. So one thing we can do, given our knowledge of half-lives, is we can set up an equation that will show us how much would be left, how much of an isotope would be left after a given amount of time, as long as we know its half-life. And here's the equation. So n equals n naught times 0.5 all to the power of t over t half. I'll explain what each of these variables represents because this is a pretty crazy looking equation. N is really just the final amount. So how much do you have left? How much of this isotope do you have left after a given amount of time? So this is kind of what your resulting amount would be. So this is after the decay has taken place. N naught is your initial amount. So this is how much did you start with? How much did you begin with? We're looking at the beginning quantity of our radioactive isotope. So just specifically the radioactive isotope. So the before the decay happens, how much did we have? Now this lowercase t in the exponent, this will represent the amount of time that has gone by. So after a certain period of time, more and more and more of it will decay. So we need to know how much time went by to figure out how much of the substance we would have left. So this is represented as the time of decay. And the t½ is the half-life. So what is the half-life of a specific isotope, or the isotope that we are doing this calculation about? Now you might look at this and think, what kind of units do I need to be using if I'm going to be using this formula? Well, the truth is it doesn't really matter as long as you follow a couple rules. First of all, the time of decay and the half-life, they all have to be some sort of unit of time. And it doesn't matter what unit of time. It could be seconds or minutes, hours, weeks, years, even billions of years. So any unit of time will work. The deal with that is they have to be the same unit of time, because they're in that fraction together and eventually will end up canceling each other out. So if you have a time unit of seconds in one of them and a time unit of minutes in another, you have to convert to keep them the same. The same goes for our n's. You can use any quantity unit, any amount unit that you want for both the n0 and the n. You can use grams. Popular one is grams, kilograms, moles, the quantity of atoms. You can use a percentage as your unit, but you have to keep in mind that both n's have to have the same unit. So you may have to convert from one unit to another if you're given different units for these n values. So it says here that the half-life of strontium-90 is 20 years. Now, if a sample of this nuclide has an initial mass of 8.000 kilograms, what will its mass be after 80 years? So we're going to start out with the equation. I'm just going to give you that equation. N equals n0 times 0.5 raised to the power of t over t1/2. And then t1/2, just remember that that represents the half-life. So it's a time. Both of those are times. Now I'm just going to plug in the information that I know. I'm trying to find the mass after 80 years. So I'm really trying to find my final n. So n will equal n0. This is the beginning. This is the initial amount. And it says that I started with 8.00 kilograms. So that's my n0, that's my initial amount. Then I have 0.5 raised to the power of t over t1/2. Now the amount of time it has decayed is 80 years. And the half-life of this specific isotope, strontium-90, is 20 years. So this is kind of how I put all my numbers into that equation. Now I'm really just going to spend the rest of this time simplifying it and doing a lot of this math. So n is equal to 8.000 kilograms multiplied by 0.5. Really that is raised just to the 4th power. This shows that we have undergone exactly 4 half-lives. If one half-life is 20 years, 4 half-lives would be 80 years. So it has undergone 4 half-lives. So I'm going to take 8.000 times 0.5 to the 4th. So I'm going to figure out what 0.5 raised to the 4th power is equal to. And it says it's equal to 0.0625. So 8.000 kilograms times 0.0625 will give me my answer. So the final mass of this strontium-90 after it has undergone decay will be equal to 0.0625 times 8, which is 0.5. And I'm going to put 2 significant figures on this just because I'm going to assume that my 20 and 80 both had 2 significant figures. So 0.5 kilograms of strontium-90 would be left after 80 years because it has a half-life of 20 years and I started with 8.000 kilograms. The half-life of carbon-14 is 5,730 years. Now, carbon-14 is the isotope that is used in radioactive carbon dating. What percent of an original sample of carbon-14 would we have after 13,000 years? And I'm going to assume full amounts of significant digits on all of these numbers, so I'm going to give it 4 significant digits. So we have n equals n naught times 0.5 raised to the power of t over t half. So when you're asked to find a percentage, you have to assume that you're always going to start out with 100% of your sample. So my n naught is 100%. And then what we'll end up with is a percentage, the percent that is left. So we have 13,000 years as the top of our fraction in the exponent, and the half-life is 5,730 years. So n is equal to 100% times 0.5 raised to the power of whatever 13,000 divided by 5,730 is equal to. Let's type that into a calculator. And we get 5,000, all right, we get 2.26876, a lot of numbers. We're just going to round that to 2.269 right now, but we'll keep that in the calculator and use it later on, rounding completely at the very end. So what that is going to equal is 100% times whatever 0.5 raised to this power would be. So I'm going to type in 0.5 and then raise it to the power of my answer from the previous math problem. So I get 0.2075 and then a bunch of numbers. So 100% times 0.2075, bunch of numbers after that, is going to be the answer. And that is going to be in the units of a percentage. So really what I need to do is take my answer times 100, because I'm multiplying by 100%, and I get 20.75% as my answer. Now keep in mind, I told you at the beginning that I'm going to include all the significant digits here, so I want to round to 4 significant digits for that final percentage. Now this next problem is pretty tricky and will require some extended knowledge of algebra. So fluorine-18 is found to undergo a 90% radioactive decay in 366 minutes. What is its half-life? So this is the formula that's used to determine the half-life of something that would be like 4.5 billion years old. We don't need to wait 4.5 billion years. We can take a small sample and use this equation to figure out what the half-life would be. So we're looking at it, and it is going to undergo 90% radioactive decay, which means that 10% will be left after 366 minutes. So I set this up, I have 10% left. I stored it out with 100%, remember, and then I plug in my 366 minutes, and I'm finding the T1/2. So I'm finding the half-life. So it's going to be tricky for me to find a variable, an unknown variable in an exponent. But we'll start with the easy stuff. First, I'm going to divide both sides by 100%. And what this will do is this will cancel out the 100% on the right-hand side and allow me to move that over to the left-hand side. And if I take 10% divided by 100%, I get 0.1. Now remember, both percentages will end up canceling each other out, so I don't have to worry about keeping that unit on there. Then what I end up with, what's left, is 0.5 raised to the power of 366 minutes over T1/2. So how do I get rid of that exponent? How do I move that exponent down into a workable space? Well, you have to do something that's the opposite of an exponent. And the operation that is the opposite of an exponent is a logarithm. So what that will do is that will move my 366 minutes over T1/2. It will move it to the outside, and now it'll be just a fraction that's multiplied by this. So I have to take the log of both sides in order to do that. So the log of 0.1 is equal to, and then I move that 366 minutes fraction down over next to the 0.5, but I have to take the log of the 0.5. This is just the property of logarithms. It allows me to do that. So now this exponent becomes actually something that I am just multiplying it by. So now what I'm going to do is I'm going to get rid of the log 0.5 by dividing both sides by log 0.5. So I'm dividing both sides by log 0.5 here, and that will allow me to cancel out the log 0.5 on the right hand side. And I can do a really easy actually math problem on the left hand side. As long as you have a calculator, this math is super easy to do. You just type in log 0.1 over log 0.5. And when I do that, I hit equal here. I get 3.3219. I'm just going to round that to 3.322 for the time being. So the log of 0.1 over the log of 0.5 gets mathematically computed, and now I got rid of all my logarithms. I'm not dealing with those anymore. So I have 3.322 is equal to 366 minutes over T1/2, which is my variable. That's the half-life of this substance. Now what I'm going to do is there's a lot of different ways you can go about this, but I'm going to set up a problem that allows me to get rid of the fractions. So I'm going to take 3.322 over 1 is equal to 366 minutes over T1/2. And that allows me to do some cross multiplying, and essentially I'm going to do cross multiplying and dividing, but I'm going to set it up as a more fractionless equation first. So I have 3.322 times T1/2, so this is my unknown variable, and that's equal to 366 minutes times 1, but I'm just going to leave the 1 out because 366 minutes times 1 is 366 minutes. So now what I can do is everything is all flat and there are no fractions involved in any of this. I can divide both sides by 3.322. And that will allow me to cancel out the 3.322 on the left-hand side. So I take 366 divided by 3.322 to get my T1/2, or to get my half-life for this problem. So I'm going to pull up my calculator here, and I type in 366. I'm going to divide that by the answer from the previous question, or the previous problem, and I get 110. Now let's look at the units for that. The units will be the same units as the units that I used for that fraction, for that time that took place. So the answer, the half-life, is 110 minutes for this problem. So the half-life of fluorine 18 based on this information is 110 minutes. So it's just a lot of extra work, but you can solve for an unknown or a variable in the exponent as well. It takes a little bit extra algebraic knowledge and a little bit of extra time, but it's completely doable to be able to solve for any unknown variable in this half-life equation.